All right, it's time. Please remember to come to the math colloquium. It's still happening, right? You all ready? All right, you get your fancy outfit on. It's going to be great. Where is it? Do you remember the room? 138. Okay, I'm going to be there at 5 o'clock. And you can go to dinner afterwards if you want to. Is anybody going to dinner? I'm not able. It's at the Flipside Burger Bar. I believe the deal is... Do you know what the deal is? Okay, good. I don't want to make promises because I wasn't sure. That's the usual deal. You pay $5 and you can order anything. Order the lobster burger or whatever. You still pay $5. And then the department will pay for the rest. All right. So we were talking at the end last time about these laws for limits, which are all familiar things. The first one was, so this is, if I have a sequence AN which converges to A, then the first rule was that the sequence CAN converges to CA. The second rule was that AN plus BN converges to A plus B. I'm writing these slightly differently than I did last time, but it's the same. Last time I believe I wrote this one as lim CAN equals CA, right? But you can write it with the arrow, doesn't matter. And then the third one was the product, AN times BN converges to A times B. And that was the third one. The fourth one is quotient. AN divided by BN converges to A divided by B if B is not 0. All right. So we did the first one last time. I want to do numbers 2 and 3. Number 4 is pretty similar to number 3, so I don't think we need to do that one. But I will just, can I just refresh our memory about, say, how we did number 1? It involves, the proof actually goes more or less like all of the sort of specific example sequence proofs, but I'm just going to write sort of the red part in the middle. You look at CAN minus CA, right? And this is the thing that I want to sort of simplify and eventually get to be less than epsilon. I'm just writing the middle part of the proof. You'll see this all in your notes from last time. But anyway, our strategy was to factor out the C, and when you factor through absolute values, you need to keep absolute values in there, all right? And then I want to make this less than epsilon in total. And so in order to make this happen, I want to sort of, well, can I just say, I want this to be less than epsilon. So we make, this is the trick, and it's the same trick that we're going to use in parts 2 and 3, which is why I'm reminding you. I want that thing to be less than epsilon. You look at this and think about how small does this have to be in order to make the whole thing less than epsilon. And so I make AN minus A less than epsilon over absolute value C. And that, if that is less than epsilon over absolute value C, that's how I make this product end up to be less than epsilon, all right? And can I make this less than epsilon over absolute value C? Yeah, because AN approaches A, AN converges to A, that means you can make this as small as you want. So in particular, you can make it even smaller than epsilon over absolute value C, all right? The rest of these, number 2 and number 3, involve similar tricks where you try as much as you can to simplify it, but eventually you have to make this and that part so small that it ends up adding up to epsilon, or in this case, it ends up multiplying up to epsilon. And I chose this to be specifically epsilon over absolute value C, because I knew I was multiplying by C here, and it would make it less than epsilon. All right, any brief questions about that? Similar tricks for the other two. Let's do number 2 then. Number 2. I'll actually write out the whole thing this time. So remember, number 2 was AN plus BN converges to A plus B, right? This is what we are demonstrating for number 2. I will begin as usual. Let epsilon greater than 0 be given. We'll find the begin such that n greater than the big N implies, all right. What should I write here? that's not a 0. I was starting to write a. Absolute value, what goes in the absolute values here? Yeah. an plus bn minus a plus b. Right. You should have the parentheses there. Remember, it's always you have absolute value and then the sequence term minus the thing that it approaches. So that's what it is. Can we do anything to simplify that? Well, I can distribute the minus sign, I suppose. So this is the red part, right? I'm going to simplify as much as I can. An, the red part. An plus bn minus a plus b. Right? We can distribute the minus sign. All right. An plus bn minus a minus b. Anyone have any other way you can rewrite this to make it a little cuter? I don't know about you. When I see this, I feel like putting the A's with the A's and the B's with the B's, right? All right. An minus a plus bn minus b. All right. And because this is another very standard trick that we're going to do all the time, although I don't think we've ever done it in other examples just yet. Because an, I assume all the way up here that an approaches a and bn approaches b. So actually, I like things that say absolute value an minus a, and I like things that say absolute value bn minus b. This right here, I'm going to do the triangle inequality. This is less than or equal to an minus a plus bn minus b. That right there was the triangle inequality. Remember, the triangle inequality says absolute value x plus y less than or equal to absolute value x plus absolute value y. This is a very important, simple trick that we're going to use often when we do these proofs, or when we do little examples. If you have absolute values and things added together, you can break up the absolute values if you use a less than or equal to sign. All right? These are not equal. You're not allowed to just break up absolute values over sums with an equal sign, but with a less than or equal, you can. All right? And now, remember, just like before, remember the one from before, I ended up, like, you can't really simplify this anymore. Now, I want all of this to add up to epsilon, and I have to think, how small do I want each of these things to be so that it ends up adding up to epsilon in the end? And we're going to do what we uncreatively call the epsilon over 2 trick. And it is, you just make each of these less than epsilon over 2, and then it adds up to be less than epsilon. So I'm going to say we need each of these, an minus a, less than epsilon over 2, and bn minus b less than epsilon over 2. All right? Can we choose the n to be big enough so that those are each less than epsilon over 2? The answer is yes, because an converges to a and bn converges to b. It means you can choose the n big enough so that those are less than anything you want. And so in particular, they can be less than half of the epsilon that was given in this problem. So this is sort of the end of the red part. I'm going to say let n be so big that n greater than n implies an minus a less than epsilon over 2 and bn minus b less than epsilon over 2. All right? Because an converges to a, you can make that, there is some n that makes that as small as you want. And so in particular, we can make it less than epsilon over 2. And we can even make the n big enough so that both of these things are less than epsilon over 2, because they both converge. I mean, an converges to a and bn converges to b. All right? And now, from here, we can just proceed with the proof as we usually would finish it off. So I say, then, if n greater than n, we have